Okay, so this is lecture 19, and up to this point we have covered a few different topics. The first thing that we've done is talk about what an observer or a navigation system is, and we've found out how to choose a matrix or a gain matrix L such that we can get an observer that looks like this, and with an initial guess x hat naught such that our x hat over time converges to the actual state. We've also gone and looked at a few types of control, the first one being a stabilizing controller. This is the controller of the form u equals minus kx, and we've chosen a gain like k using Ackermann's placement method, which we've also used to go and choose L. The connection between these two, and the reason why we go and often consider state feedback and not just state estimate feedback, is by virtue of the separation principle. We then went and considered how we could actually not just use a controller like this to drive our system to zero as an equilibrium point, but also to drive it to some sort of desired state or desired output. We called that reference tracking.
Oh, that smells.
And that input was of the form u equals minus kx plus a reference gain kr times our desired output zd. And then finally we talked about integral control or integral action, wherein we introduced a new variable ez that integrates the difference between our desired output and our real output over time, and then includes a new controller that on top of our k minus kx gain and maybe a reference gain like kr times zd also includes an integral gain ki times the times ez, which is the integral of the difference between our output and desired output over time. This material is all you need to know for our midterm on basic control design. So this is midterm 2. The topic of today's lecture is to give you some information, some supplementary information that is in practice quite useful when using some of these rules to design navigation systems and controllers. And in particular, we focus on 3 different topics. One is an alternative prediction method in a navigation system that most aerospace products use. The second is an issue in actuator saturation, which requires a little bit of a change to our PID controller that we call integral windup. And the third is in communicating or drawing our control systems, and that's done through the practice of block diagrams, which many people find very useful. And so we'll work in backwards order here. So we'll start with block diagrams, or drawing your control system out. And the way we're going to start is by having our control system expressed in terms of blocks. And each of these blocks does an operation and it does an operation on inputs, and it produces, as a result of that operation, some sort of output. And inside is defined either our controller, our navigation system, our state space system, and so on. So for example, for our state space system, we might have our state and output expressed. And in this particular case, our input, it might be the control that we apply, and the output is what our sensor provides, Y. What this diagram then shows you is what you can give your system and what you get out. In other words, the state here operates within the system, but you don't get to see it either on the output or on the input side. In other words, you would have to estimate that, which is, I think, one of the reasons why block diagrams communicate control so well. One other commonly used component of a block diagram is a summing junction or a subtraction junction, and this operation is drawn as a circle and often has two inputs, maybe an x and an x hat, for example, and you can have one of these inputs added and the other subtracted to get x minus x hat as the output. Alternatively, I could have both of them summed and the output would be x plus x hat. Or I could have this one summed and this one subtracted, and I would get minus x plus x hat. So we'll just go back to here. Okay. If we go back then and try to design some of our controllers with this, what we can do is we can start with our normal state space system that describes all of the dynamics of whatever it is we want to do, apply a controller or a navigation system to, and the outputs that might come from sensors or what have you. And so we have an output coming here and an input coming in, and we have to choose what to do with our output and how to go and apply our input. This system right here, because it describes the dynamics of our system, is often called the plant in terms of the block diagram. And what we typically do, as you know, is we take our output and our input, and apply it as the input to our observer. X dot, or x hat dot, comes out, and we might find x hat at some additional point using something like Euler's method. And so as a result, we have x hat t, which can then also be applied back here. And so what we see here is that we have as inputs to our observer a y, an input, and some sort of guess. And then to guess the next output, we apply Euler's method, or the next state estimate, we apply Euler's method. And so this system right here is the navigation system. And again, Euler's method can be substituted with all sorts of different numerical integration methods. To apply control here, we might take that estimate and multiply it by our control gain to get our stabilizing input U, which is very common. If we wanted to have a desired output ZD, we might multiply this. Let me draw this. If we had some sort of desired output ZD, we might multiply this, and then add the result of our stabilizing controller and our reference tracking controller to get our new input, U. Okay, and so now we have a navigation system on the bottom here, all that stuff, and then on the top here we have our control. And so this control here is also expressed as U equals minus kx hat plus kr zd. Notice that in this particular case, I could have taken these boxes and actually collected them together as one bigger box, just as I did with the observer here. And likewise for the observer here, I could have broken this into smaller boxes, one that describes AX with a summing junction like this to get AX plus BU, and then plus a correction term. Likewise, I can add an integral term on the difference between some sort of output and the desired output, and then apply my integral gain to get a similar result. If I actually wanted to find what my current output was, or dummy output was, in comparison to, say, my sensor output, I might take my state estimate and apply H times x hat. This is assuming that it's not a function of an input, to see what my actual desired output, or my actual output estimated is. Again, if x hat converges to x over time, z hat will converge to the actual z. And if I choose a controller well, hopefully z hat also converges to zd, my desired output. Okay, so this is in general how we go and draw our control systems, and this will take practice to do, but for those of you that think visually, this is a nice way in which you can draw these sorts of control and navigation systems. So every time you go and design one, particularly for your project one, you may want to consider drawing that guy out as a way of expressing what you've done. Okay. The second topic that I want to talk about is actually about actuator saturation and PID control. And remember that PID control looks something like this. I think I used x tilde last time, minus kd x tilde dot minus ki integral x tilde over time notice that if, for example, I have some sort of airfoil, and at the end of the airfoil I have some sort of flap that hangs off like this, and this airfoil can be pushed up or down at an angle theta. It can't be typically pushed at any angle theta, and that's because you have some sort of actuator here that'll push it up, and that actuator can only stretch or shrink a given amount. So there's a range that any actuator can apply, and it looks typically something like this. If this is my commanded input, say UC, and this is my actual input, U, I'll typically have a 1-to-1 ratio between commanded input and actual input. In other words, if I command U1, I'll get let's call it UC1, I'll get out U1, and in this case U1 will equal UC1. And that can happen all along this line. In other words, it has a slope of 1. At some point, though, it will saturate. In other words, as I increase my commanded input, the actual input won't change. That's because an actuator like this can't extend any further or shrink any further than a certain amount. And that's why you also have this, it won't go out, let's say to UC and U4, but we'll only have a certain minimum. Okay. Here I drew this having a negative input. Sometimes it'll all be positive, sometimes it'll only be negative. It depends on how you define the coordinate system. But you'll always have some sort of 1-to-1 slope, and then a saturation, and then a saturation. This is just a fact of reality, I guess, but it poses a bit of a problem with this integral term because you can imagine that if I have a system and its output plotted over time, and here's my desired state, I might have my system go up, come down like this, and if my U, my input, saturates at this level, and it saturates at this level because we have a U that's equal to minus kx, let's say. So it's a function of the output. In fact, we can just say that it's kz minus zd just to make it even more explicit. If I were to then integrate the z minus zd over time, even if this were to what would happen, well, let me illustrate this. What would happen in terms of time is if I had T1 and T2 with this kind of control, if this were my input, then I might have a U of saturation. You might go up, and hit a saturation point and stay there between T1 and T2, because I can't get any bigger than this, and above here my Z minus ZD causes you to hit a saturation point. An integral term, or adding an integral term to this, can cause a bit of a problem, because not only will it go to saturation faster, which just tends to be a fact of life with integral controllers sometimes, but when you actually go and account for what happens during the point of saturation, you accumulate all of this error into here. And so even when you come below the point of saturation where your constant gain is, you may remain saturated beyond the normal point. In other words, you may be saturated up until T star rather than T2. You may be saturated longer than you need to. Why? Because I need to, before getting below the saturation point, accumulate an error in the negative direction. But actually, not even here. It would be below my ZD up until I hit a space that's equal to up here to prevent saturation. Okay. And this, by the way, to prevent saturation, ignoring again for a second the difference of K minus of Z minus ZD here, right? So there has to be a sum that goes above the saturation point. Anyway, what this means in practice and why it's a practical issue for us is because in order to prevent this wind up of the integral term during a period of saturation in our control input, in other words, in the point where the integral term can't actually help anymore achieve our control objectives, we need to make sure that our integrated error doesn't wind up. In other words, we don't want it to integrate anymore. So if U goes beyond the saturated input, or if U is less than, let's say this is a saturated maximum and this is the saturated minimum, then we need to turn off the integral here. On a computer, or like in a MATLAB program, this is actually not that hard. There are a few different options. One is to record the time at which you are above or below the integral, and then simply, or above or below the saturation point, and then simply turn this into two integrals. One that goes up to the point of saturation, okay, and then a second one that takes place after the saturation has ended. And that'll prevent you from doing the accumulation. Another one is to simply start, is to have your standard integral, and then to add a subtracted integral once you hit saturation point, hit a saturation point as well, and to stop the subtraction once you end the saturation period. So there are a few ways to do this in practice, and in code it's not quite so difficult to do. But the important thing is that no matter what you do, if you have a saturation of your actuator, then you simply want to turn off the accumulation of your integral. It's called integral anti-windup. Okay, the last topic I want to talk about is alternative prediction methods to navigation systems. And in particular, I want to talk just a little bit about inertial navigation systems. And I do this just so that you've seen this, so that it's not a little bit confusing than the first time you actually have to use this, if you ever have to use this. And recall that our navigation system looks like this. And then when I actually estimate x at a certain period, x at a certain period of time, I simply have to integrate x hat over time, or I guess with respect to tau, from the initial to the current state, right? And we can do that with something like Euler's method. But nonetheless, we have an observer of this form, typically is the way that we state this. And this has two parts. One is what we call prediction, and the other is correction. And here I say that it's minus cx, but keep in mind that it can actually also be cx hat minus du. So in other words, there can be a measurement that's related to the input. You can see that as us measuring the what the actuators are actually telling us, as opposed to what we think we are commanding. We'll focus now on the prediction piece of that. We typically have considered y to be what is measured by sensors, and in fact you've seen that in the homework. Those our y measurements were part of a sensor struct. And we use our state space dynamics, or our model, to make this prediction, right? In fact, this looks just like the state space form. So that if we have an x naught that is actually correct, an initial guess of our state is actually correct, the solution to the prediction will be equal to the state over time. The correction doesn't actually need to do any work. In practice, that's very hard. And just like we talked about before, that there is a difference between a model and reality in control, that difference also exists in observers. In other words, when we go and make a navigation system, there's a difference between our real state space system and the one in which we're modeling. And aerospace engineers deal with this difference by using an inertial navigation system. And what does this mean? Well, what it means is that rather than applying a model like this to do prediction, we actually use a series of sensors to do that. In other words, the sensors in normal aerospace navigation systems aren't just applied to get y, they're actually also applied to do the prediction. Let me describe why that works. Recall that if you have some sort of object like a rocket, or an airplane, or a satellite, and so on, you typically have a few things that you have to consider. You have to consider, number one, Newton's laws. In other words, F equals ma, and you have to consider Euler's equation. And Euler's equation is omega is equal to the inverse of the moment of inertia times torque minus the angular velocity crossed with the moment of inertia times the angular velocity again. This you can think of as just Newton's equation, or Newton's law, expressed for orientation as well as position. Think about all the error that exists when forming a state space. Well, let's first form the state space. First of all, we can express our position in terms of x. And so if we have x, and we'll have x hat as our state, and we might have an angle theta, or a set of angles theta, and theta dot, which theta dot is going to be equal to omega in this case. If we were to actually go and express the state space system, okay, we end up with something like this, and this actually is the same as our angular acceleration. What this means is, well, number one, the top line is actually equal to one of our states already, but the second one we actually need to set to be equal to F over ma. This is actually equal to one of our states already. It's equal to omega. And the second line we actually have to go and apply Euler's equation. This, if linearized and then applied to our method of prediction, so that we get a modeled ax plus bu, and we do the same with our sensors to get cm and dm. But since we're only applying prediction here, we only care in this case about a and b. If we do this, you can imagine that error doesn't actually accumulate from the integration of x of our state, or the integration of our angular velocity, unless it comes from numerical integration error. Rather, error in our prediction, beyond just a bad state estimate, can come from measuring the moment of inertia wrong, or measuring our torques incorrectly, or not knowing our mass quite right, or not having a perfect model of the forces. If you think about an airplane or a rocket, mass varies with the amount of fuel consumed. So does the moment of inertia. And forces and torques can be a little bit complicated to model because of all the different kinds of aerodynamic flow that's going around the aircraft, rocket, and so on. Or even on a satellite, the dynamics can get a bit complicated. And error can accumulate in the prediction process simply because your model does not reflect the reality of your state space system very well. Just like we dealt with this difference with controllers, in the controller case by including an integral term, we can deal with this as well in navigation systems. But in terms of navigation systems, we introduce a sensor. And that sensor is typically, in aerospace applications, an IMU. And an IMU measures two things. First of all, it measures specific force, and it measures omega. Now, omega is exactly one of our states, which is great. The specific force is almost equal to x double dot, except that it doesn't measure gravity. In other words, x double dot is equal to the specific force plus gravity. So, if we actually wanted to go and now make our prediction, of x and velocity x, then we can simply integrate x double dot, which is integrating the measurements from our IMU plus gravity over time. We get these measurements at a very quick rate, and we can estimate gravity because we will have an estimate of the orientation. Once we have an estimate of velocity, we simply integrate our estimate of velocity to get position. This is no different than what we do for a normal system, even without an IMU. On the orientation side, in order to get our theta over time, we simply have to integrate our orientations, or our angular velocities. It's not quite as it's not quite as straightforward as this, because as you integrate this, orientation changes, and as you integrate this, this has to be actually multiplied by changes in orientation. And if you've dealt with dynamics before, you may have seen how you need to do this. You need to multiply this, or in other words, you need to multiply this by rotation matrices R, or you need to multiply this by some sort of matrix S times theta, and S is a function of theta, and so on. We won't deal with these details. This is again just supplemental information. I provide a reference on more details on how this is actually done in practice, but the point here is that sensors aren't just used to apply correction, but they can actually be used to predict as well. And so, if I were to draw out the process here, I would have my prediction process, which I could talk about as integrating omegas and integrating ASF plus G to get a predicted x hat. And I might have IMU measurements, omega and ASF as my inputs. And then I might add to that a correction term, L, Y minus CX hat. To get how I should change x hat, well, this should be the predicted x hat dot, to get my predicted x hat dot added to the correction term yields the resulting x hat dot for my navigation system. I can then apply some sort of integration method, x hat dot, to actually get x hat. If I get my output y from the plant, so if I have, for example, some sort of plant, x dot equals ax plus bu, and y equals cx plus du, then I might have y coming out, and I might have an input u, and my estimated state would then be applied to the correction. And it can also be applied to the prediction, because the prediction needs a starting point as well. And so this is the resulting navigation system that people use in practice. Again, all of this is useful information that you can use when actually implementing these systems. You can go and implement some of these things in practice in some of your projects, the most useful one I think to start with is to try to draw yourself a block diagram as a way to communicate the control architecture that you've chosen. And of course, if you need any help with that, you can let me know on Piazza, and we will work through it. But with that ends the second part of this course, which is designing basic navigation in control systems. And in the next part of the course, we will focus on designing optimal linear control systems and navigation systems.